Some math YouTubers started a project called MegaFuff Numbers, where they talk about their favorite number over 1 million. I thought that's a neat idea and I watched a few of them, but then it clicked. I also have a favorite number over 1 million. There's actually a reason why I didn't realize it at first, which I will also tell you about. But for now, here it is. 1,094,795,585. This number has a special meaning to many computer hackers, and I want to show you why. To understand what is special about my number, let's first look at the rule of this YouTube trend. A favorite number over 1 million. We are quickly drawn to this kind of number. There are shows like Who Wants to Be a Millionaire, or we say things like not in a million years. It's a nice number and we seem to gravitate to it. One of the reasons is probably because it's quite aesthetic. It's very simple, a 1 with 6 zeros. Every child can write it. But it only looks this neat because our numbers are decimal numbers, written with 10 symbols going from 0 to 9. We also have other number systems, such as binary, only using 2 symbols, 0 and 1, or hex, which uses 16 symbols, using 0 to 9 and adding the letters A, B, C, D, E, F to it. 1 million in binary looks not special. In hex, it's also quite ugly, F4240. There's nothing special about this number anymore. It looks random. The same way how my favorite number looks random in decimal. So let's look at my number in hex representation instead. That looks a lot more aesthetic. 41414141. A nice pattern. We immediately would say, yeah, that's pretty neat. So let me first try to make you appreciate hex numbers, why they are useful, and thus why programmers, hackers, and other people interested in lower level computing stuff love hex so much. Hex is a number system where we represent values with symbols from 0 to 9, A to F. So let's count. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And like in decimal, when we reach the highest symbol we have available, we start to combine symbols. 1, 0, 1, 1, 1, 2, and so forth until 1F. And then, like a decimal 19 that would wrap over to a 20, after a 1F, we would roll over to a 20. By the way, I'm intentionally not saying 20 when I refer to the hex number. Instead, I say 20 because I want to make it clear that this is not decimal 20. The value of a hex 20 is actually a decimal 32. This might seem unnecessarily confusing. Why would we want to use hex if it means we have to get used to a different number system? Why would anybody do this? What makes it so incredibly useful? Well, let's look at the relationship between hex and binary. As probably everybody knows, computers use zeros and ones. The CPU you most likely have inside of the device you watch this video on has tiny memory cells we call registers, which store 32-bit or 64-bit binary values. And the CPU can use these registers to perform calculations. So you might think, if we want to deep dive into a computer and want to observe exactly what the CPU does, it might make sense to look at the binary values. But a 32-bit or even 64-bit binary value is long. It takes a lot of space and it's very hard to quickly understand what is written there. But what if we could group up binary values to save space? For example, take them as a package of 4 bits. Let's list all possible values. 0000, 001, 0010, 0011, and so forth up to 1111. Directly translating them to decimal would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But now we have a problem. In decimal, we don't have any symbols left to represent the remaining 6-bit groups. Let's see how these binary values converted to hex would look like. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. 4 bits nicely match to a single hex digit. You might also know that a byte consists of 8-bit, so a byte can easily be represented by 2 hex digits. Let's do an example. 1010, 0101. we split the 8-bit into two 4-bit groups. This is an A and this is a 5. A5. And in reverse, it works the same way. What would be a hex FF in binary? Well, F was the highest value, so 1111, which means the byte FF is in binary 11111111. We also have a name for this subgroup of 4-bit inside a byte. We typically call this a nibble. This is pretty neat, right? A single hex digit is a nibble, 4 bits. 2 hex digits make up a byte, 8 bits. And 8 hex digits, or let's better say 4 times 2 hex digits, are 4 bytes, or 32 bits. So, my favorite number is actually a 4-byte value. And in fact, it's 4 individual bytes put together. Looking at my number in decimal again, we can clearly see there is no pattern here. Simply by looking at it, it doesn't tell us anything meaningful about its underlying structure of bits. So hex is so much nicer. We know it's repeating the bits represented by 41. But what is special about the hex value 41? Well, there is a character encoding standard called ASCII, American Standard Code for Information Interchange, and it's basically a big table that we just agreed on to use. And it tells us if we have a series of bytes and we want to interpret that as a text, how do we map those bytes to actual letters and symbols and numbers? And hex 41, or decimal 65, maps to the capital letter A. So my number is actually the string AAAA. And that's also why I didn't immediately realize that this is a number over 1 million. When I read the hex value for 1, I'm not thinking of an amount. But when I see 1 million in decimal, I think of 1 million of something, $1 million, 1 million light years, 1 million views. But I'm not thinking of hex for 1 as a billion of something. When I see that number, I see 4 bytes. I see the characters AAAA. Okay, now you know why hex values are useful for computer science and why we like to use hex. It's so much easier and nicer to represent anything that has to do with bytes and bits. But what is special about my AAAA sequence, 41414141? What does it mean to me? What does it mean to hackers? Let me show you FRAC. FRAC is an e-sign written by and for hackers, first published in 1985. The best and by far longest running hacker sign. The magazine is open for contributions by anyone who desires to publish remarkable works or express original ideas. It has a wide circulation which includes both hackers and computer security professionals. And let me pull up one of the most famous articles in here. It's in issue number 49 from 1996. Here it is, Smashing the Stack for Fun and Profit by a hacker named Aleph1. When I read this, I actually get a bit emotional because it's a very impactful article in the history of hacking as it summarized and publicized the intricate details of buffer overflows and how you can use them to create exploits. On many C implementations, it is possible to corrupt the execution stack by writing past the end of an array. This can produce some of the most insidious data-dependent bugs known to mankind. This article explains very detailed how programs written in the programming language C are being executed by the CPU, and further down it then introduces what happens if you have a buffer overflow vulnerability. A buffer overflow is the result of stuffing more data into a buffer than it can handle. How can this often found programming error be taken advantage of to execute arbitrary code? This example C program has a loop where it executes this line over and over, and this builds a huge string of A's. It keeps appending AAAA, and then it copies this 256 long A string into a very small memory area of only size 16, which causes the AAAA to write beyond what was intended. And in this process, it will overwrite other values in the computer's memory. If you run this program, you will get a segmentation violation. If we analyze this with a so-called debugger, that is a program that can help us to observe instruction by instruction how the CPU executes this program, we can see that we reach a segmentation fault because the instruction pointer got overwritten by hex for 1. The instruction pointer is a very small memory cell, a register, inside the CPU that contains the memory address of the next instruction to be executed. and our buffer overflow apparently overwrote a value in the computer's memory that caused the instruction pointer to be overwritten, with a value we control. We created this long string of AAA, which means if we carefully change a specific part in this long string, we can cause this instruction pointer to be set to an address we want and redirect the code execution by the CPU to memory we want. We can hijack this process and execute our code. This is very complicated when you do or see this the first time, but it feels incredibly magical to pull this off. So if you are interested to learn more in detail how buffer overflows work, I've actually a playlist called Binary Exploitation, where I use a test environment from Exploit Education to walk you through various stages of learning buffer overflows. But just FYI, the course is mostly intended for people that already have some programming knowledge. But if you just want to see some crazy examples how to analyze, find, debug, and exploit a buffer overflow, I also link some video of mine from participating in capture the flag hacking competitions. Anyway, in this Frag article, you can see this hex for 1 for 1 for 1 for 1 showing up. And I'm not sure if this is the first occurrence of this, but all I know is since then it has somewhat become a symbol in itself for buffer overflows and binary exploitation. Just Google for hex for 1 for 1 for 1. All you will find is buffer overflow examples. It is used in the book Hacking the Art of Exploitation. A famous German hacker going by the name Affix uses for 1 for 1 for 1 as a handle. In presentations at security conferences where they show off vulnerabilities they found in software, they use hex for 1 for 1 for 1 for 1. Every security professional who sees this number understands that this is attacker-controlled input and they were able to control a critical memory value and set it to any value of their choice. AAAA is a stereotypical input somebody uses to showcase buffer overflows. It was the input I have used the very first time I tried to learn and understand buffer overflows. I connect with this number a very emotional memory, this magical moment when I did my first buffer overflow. And that's why it is my favorite number over 1 million.